This lecture is a continuation of the previous lecture on trust region methods, where we have described a general structure of trust region algorithms and also got to know how to execute approximate solutions of the trust region subproblem at each and every given iterate xk by executing Cauchy step, dogleg step and double dogleg step. In this lecture, we will consider to execute a numerical example with the help of the dogleg step and also provide the global convergence analysis of general trust region method. A general structure of trust region methods that we have gone through in the last lecture is this one, which is having in total 5 steps. Out of these 5 steps, the most important step is this step 2, where we calculate a trust region step by solving the trust region subproblem at the current iterate xk. If execution of an exact solution of this trust region subproblem is not easy, then we can go with an approximate solution, provided that approximate solution is having a sufficient decrease property, which is identified by this inequality. To identify an approximate solution to this trust region subproblem, so that in that approximate solution we have this property, we have gone through the concept of Cauchy step. For the Cauchy step, we have got to know in the last lecture that the Cauchy step satisfies this sufficient reduction condition with beta 1 is equal to half. We also have an interesting fact about the dogleg path, which is the following. If we move from the trust region center towards the Newton direction through the Cauchy point, then the model function value decreases along this path. And therefore, if at the Cauchy point this sufficient reduction condition holds, then certainly for the dogleg step we also will have this sufficient reduction property. And therefore, instead of considering PKE the exact solution of the trust region subproblem, we can employ the dogleg step to be taken here. As dogleg step is always on the boundary of the trust region, we have to revise the step 4 of the general algorithm, where we check that whether the trust region step is on the boundary or strictly inside the boundary. These two portions are to be removed from this step 4, and if we employ the dogleg step instead of the exact trust region step, then we name this entire algorithm as dogleg trust region method. Let us now execute two consecutive iterates of a numerical example with the help of dogleg step. Before moving to the numerical example, let me mention afresh the terms that we have used so far in the description of trust region methods in the X space and in the P space. We notice that the X space is the space of original variables, original argument variable of the objective function f, and P space was defined by the transformation P is equal to x minus xk. In the P space, the trust region is represented by this set, and in the X space, this is the representation of the trust region. Any vector in the X space will be referred as a point, and any vector in P space will be referred as a step, and therefore PKC will be called as Cauchy step, while the corresponding point in the X space, that is XKC, will be referred as Cauchy point, which is given by xk plus pkc. Similarly, PKD will be referred as dogleg step, and the corresponding point in the X space XKD will be named as dogleg point. Similarly, XKDD is dogleg point and PKDD is dogleg step. PKN is full Newton step or just full step, and XKN is full Newton point or just full point. So these are the appropriate terminologies to be used in describing trust region method. Well, now next let us move to solve a numerical example. We consider the objective function of the problem as this one. The initial point is x naught and other parameter values are as given in this screen. Let us now attempt to calculate the next iterative point x1 with the help of the dogleg step. The process of calculating dogleg step is the following. At first we check whether the point x0 is a stationary point or non-stationary. To check it, we need to calculate the gradient, and the Hessian matrix of the objective function is therefore the gradient value at the point x0 is given by whose norm is equal to 27 greater than epsilon, and therefore x0 will be considered as a non-stationary point. The Hessian matrix at x0 is, in order to calculate the dogleg step, we need to consider a Hessian approximation which is positive definite. As h0 is already positive definite, we don't alter it and we just consider the same matrix as our b naught. To calculate now the dogleg step, at first we calculate the cos step. The cos step length alpha naught c is equal to minimum of 1 by 45 and 1 by 46, and therefore is equal to 1 by 46, and therefore the cos step is equal to minus 0.587, and the full Newton step is, let us calculate PC naught norm, which is equal to 0.587, which is less than delta naught, because delta naught is 3 by 5, which is 0.6, and also you note that the norm of Pn naught is equal to 0.611, and therefore the dogleg step will be the intersection of the line segment joining the Cauchy step and the Newton step together with the boundary of the trust region. Let us try to locate the locations of the Cauchy step and the Newton step in the p variable space. P has two components, P1 and P2. Let us suppose this is the axis of P1 and this is the axis of P2. The center of the trust region is origin in the p variable space, and the radius of the trust region for the current iterate x0 is equal to delta naught, which is equal to 3 by 5.6. So we draw a circle of radius 0.6 centering at origin, and the location of the Cauchy step inside this trust region is in the negative P2 axis somewhere over here, and the location of the full Newton step is in the third quadrant somewhere over here, and the dogleg step is the intersection of the line segment joining the Cauchy step and the full Newton step with the boundary of the trust region. And here the dogleg path is this line segment and this line segment. Together, these two line segments are constructing the dog leg path. We notice that the dog leg step is then this point P naught D, which can be presented as a convex combination of the Cauchy step and the full Newton step. So this will be the expression of the dogleg step for some tau in between 0 and 1. So the dogleg step is identified by, so we find the tau such that this equation is holding true. This equation will give us a quadratic equation given by 22 tau square plus 7 tau minus 16 is equal to 0, and tau has to be in between 0 and 1, and accordingly we get the value of tau is equal to 0.708, and hence the dogleg step is P naught D is equal to, after calculating the dogleg step, a Trust-Region step, we go for computing the reduction ratio value. Reduction ratio value will indicate whether to accept or whether to reject this Trust-Region step to compute the next iterate. The reduction ratio value is ratio of actual reduction and the predicted reduction. Actual reduction value is equal to the difference fx naught minus fx naught plus p naught d. Predicted reduction value is m naught 0 minus m naught p naught d, where the model function m naught is given by 11 plus 27 p2 plus 23 p2 square, where this p has two components p1 and p2, and accordingly we obtain the value of the reduction ratio as 9.504 divided by 7.923, which is equal to 1.199, which is greater than the threshold, and therefore the next iterate is given by x1 equals to x naught plus p naught d, which is equal to, now to revise the Trust-Region radius, we need to check whether the reduction ratio value is bigger than the happy threshold or not. We notice that this reduction ratio value is even bigger than the happy threshold value eta 2, and therefore according to the step 4 of the dogleg Trust-Region algorithm, we need to expand the Trust-Region radius by calculating minimum of maximum most value of delta and twice delta naught, which is equal to 1. After calculating x1 and delta 1, we go for checking the stationarity of x1. If stationary, then we stop, and if not, then we again proceed to calculate all the steps that we have calculated here to find the next iterate x2, and so on. Keep continuing this process until we find an iterate xk at which the norm of the gradient is less than epsilon. In the next, let us now prove the global convergence result of the general Trust-Region algorithm for the cases where we employ the Trust-Region step in the step 2 of the general algorithm as any of pke, pkc, pkd or pkdd. In fact, at the end of the proof of the global convergence result, we shall see that if we employ any of the points inside the Trust-Region at which we have a sufficient reduction condition holding, then the global convergence result will be followed. A sufficient reduction condition at a given pk inside the Trust-Region is identified by this inequality. This inequality we have seen that is holding to be true for the Cauchy step with beta 1 is equal to half. Well, for the Cauchy step this inequality is holding. Then how about this inequality of sufficient reduction for pKe, pKd and pKdd? Well, for pKe it is very trivial to realize because at pKc this condition is holding, and pKe is the minimum-most point of the model function inside the trust region, and therefore we have this inequality, and accordingly as at pKc we have the sufficient reduction condition holding, at pKe also the sufficient reduction condition will be holding. Well, then for pKd, do we have such sufficient reduction condition holding? The answer is affirmative due to two fascinating results. Those are stating that along the dogleg path, the model function value decreases, and as well along the double dogleg path, the model function value decreases. And therefore, we can eventually take any of the points inside the trust region and in the dogleg path after the Cauchy point. So we consider any pk in between this Cauchy point till this intersection of the line segment joining pkc and pkn. You will find that at that pk you have model function value less than equal to the model function value at pkc. Similar result is also true for the double dogleg path. We consider any point in between the double dogleg path in between pkc and pkn, and inside the trust region you consider any point over here as pk. Then at that pk you have mkpk less than equal to mkpkc, and we notice that in particular the dogleg point is inside the trust region and lying in between pkc and pkn, and as well the double dogleg point is located over here which is in between pkc and pkn, and therefore at the dogleg step as well as at the double dogleg step the sufficient reduction condition is holding to be true. Now next, at first we prove that you consider any pk for which you have mkpk is less than equal to mkpkc is a descent direction of the objective function. We eventually will prove that gk transpose pk is less than 0 when pk is satisfying this inequality. In proving this less than 0, we will obtain an inequality which will be conducive to prove the global convergence result. So let's start. We at first prove that at a pk for which you have this inequality is true is a descent direction of the objective function. Before stating this result, we recall the third standing assumption in discussing the trust region algorithms. It was regarding the Hessian matrix of the objective function. We have assumed that with respect to a matrix norm, the Hessian matrices are bounded by beta for some beta greater than 0. Here we also recall that while constructing the sequence of approximations of the Hessian matrix, we have assumed that all the bks are symmetric and this sequence is uniformly bounded. There is no loss of generality if we assume that norm bk is also less than equal to beta, the same beta that we have used in the third assumption. The global convergence results are dependent on these two particular assumptions. Now we go for proving that if pk be a point in the trust region such that mk pk is less than equal to mk pkc, then we have the gradient transpose pk is less than equal to, provided you have norm gk is greater than equal to epsilon and the trust region radius is less than epsilon by 2 beta. Let us prove this result. To prove this result, we recall the formula for the Cauchy step, and therefore this inequality mk pk less than equal to mk pkc gives us fk plus gk transpose pk plus half pk transpose bk pk less than equal to mk pkc. We see that when norm gk is greater than equal to epsilon and delta k is less than epsilon by 2 beta, the Cauchy step pkc is given by, this is due to a very trivial fact that if you have gk transpose bk, gk is less than equal to 0, then in that case you have delta k by norm gk, then obviously pkc is given by this quantity. If however gk transpose bk, gk is greater than 0, then we see that delta k less than epsilon by 2 beta is less than epsilon by beta is less than norm gk divided by beta, which is less than norm gk cube divided by gk transpose bk gk. Just apply the Cauchy-Schwarz inequality, you will obtain this. Therefore you have delta k divided by norm gk is less than equal to norm gk square divided by gk transpose bk gk, and therefore even if you have gk transpose bk gk greater than 0, then the minimum most value of these two quantities is equal to delta k by norm gk. So in any of the cases gk transpose bk gk is greater than 0 or less than 0, alpha kc is given by delta k divided by norm gk, provided these two conditions are holding. And therefore as these two conditions are taken into account in the hypothesis of lemma 4, we have mpkc given by this quantity, and hence mkpkc is equal to fk minus delta k norm gk plus delta k square divided by 2 gk transpose bk gk divided by norm gk square. and it will now imply GK transpose PK less than equal to minus delta K norm GK plus delta K square divided by 2 GK transpose BK GK divided by norm GK square minus half PK transpose BK PK, which is further less than or equal to by the Cauchy-Schwarz inequality minus delta K norm GK plus delta K square divided by 2 into beta plus half beta into norm PK square. As norm PK is less than or equal to delta K, we have this quantity further less than or equal to minus delta K norm GK plus delta K square into beta. Now we notice that in the hypothesis we have assumed norm Gk is greater than equal to epsilon and delta K is less than epsilon by 2 beta. Delta K less than epsilon by 2 beta gives us delta K less than epsilon by 2 beta less than norm Gk divided by 2 beta, which further gives delta K square into beta less than delta K times norm Gk divided by 2, and hence here this Gk transpose Pk is further less than or equal to minus delta K norm Gk divided by 2, and therefore Gk transpose Pk is obviously less than 0, and hence Pk is a descent direction for the objective function. With the help of this result, we shall now prove that there are at most a finitely many unsuccessful iterations between two successive successful updates. That is, if I have found one index, say k1, for which row k1 is greater than eta 1, then it will not happen that after the index k1 indefinitely for all the indices row k1 plus 1, row k1 plus 2, all these reduction ratios are less than eta 1. So after finding an index k1, after at most a finitely many iterations, you will again find k2 for which row k2 is greater than eta 2. And in fact, this result will prove the global convergence result. Now, to prove this result that there are at most finitely many unsuccessful iterations between two successive successful updates, we need to prove one auxiliary lemma which states the following, that if we consider that eta 1 value is at least 1 by 5 and not more than half, and pk be one step in tk such that the model value at pk is less than equal to the model value at pkc, and norm gk is greater than or equal to epsilon, and the trust region radius is less than a fraction 1 minus 2 eta 1 divided by 1 plus eta 1 times epsilon by beta, then we must have the reduction ratio greater than eta 1. We will not prove in detail this result. In order to make you involved in the proof of the results, let you sit with a pen and paper. I will give hint for the steps to arrive this result. Well, so here we need to prove that the reduction ratio rho k is greater than eta 1. Reduction ratio, as you all know, is given by this expression fk minus fxk plus pk divided by mk0 minus mkpk. Now for the numerator, you apply twice the mean value theorem and obtain it to be minus gk transpose pk minus half pk transpose Hessian at z times pk, where z is a vector lying in the line segment joining xk and xk plus p, and the denominator value is equal to minus gk transpose pk minus half pk transpose bk pk. Now we notice that, and therefore rho k is greater than or equal to, which with the help of the inequality for delta k can be proven that is greater than or equals to eta 1. I am keeping it as a home task. You please try to prove it. These result then confirming a very interesting fact, that is the next lemma. We neatly state the lemma, which is as follows, that we let the eta 1 value is in between 1 5 and half, then there are at most log 1 by gamma 1 delta bar times 1 plus eta 1 into beta divided by 1 minus 2 eta 1 times epsilon at most box of this quantity. This many unsuccessful updates between consecutive successful updates. The proof is very straightforward, which is followed from the previous lemma. To prove it, let us denote this integer as, let's suppose, p, and then we show that if the iterations xk plus 1, xk plus 2 and so on till xk plus p, or rather let me consider xk naught plus 1, xk naught plus p are unsuccessful, then the next iterate must be a successful one, because then we notice that delta k naught plus p plus 1 is equal to gamma 1 times delta k naught plus p, which is further equal to gamma 1 square delta k naught plus p minus 1 and so on, which ultimately ends up with gamma 1 to the power p plus 1 into delta k naught, and which is less than or equal to gamma 1 to the power the quantity inside this box, and let us call it to be t, times delta k naught, and which is less than gamma 1 to the power t into delta bar, and this quantity is equal to 1 minus 2 eta 1 divided by 1 plus eta 1 into epsilon divided by beta, and therefore delta k naught plus p plus 1 is less than this much quantity, and therefore from the previous lemma we certainly have the reduction ratio value at the iterate xk naught plus p plus 1 greater than eta 1, and hence x k naught plus p plus 1 is a successful iterate, and hence the result follows. From these two consecutive lemma we have a very important note, which is the following. Both of the lemmas together ascertain that the trust region algorithm cannot get shrinked to a non-stationary point that is, simultaneously it cannot happen that norm gk is not converging to 0 but delta k tends to 0, as this cannot happen. I am keeping it as a home task. Find why. The enough clue is the previous two results. Now with the help of this note, or rather this lemma, that in between two successful updates we have at most a finitely many unsuccessful updates, we now prove the global convergence result, which states the following: that if we consider the threshold value for the reduction ratio eta 1 is in between 1/5 and half, and the three standing assumptions that we have taken during the discussion of the trust region algorithm, those are holding, and also we consider that the trust region step pk in the second step of the algorithm be such that mkpk is less than equal to mk's value at the cos step. We are under this assumption, and therefore the sufficient reduction condition will be holding. Under these three assumptions we have either the first one is true or the second one. The first one is stating that the algorithm terminates at some finite iteration number. That means there exists some k naught, an index at which the norm of the gradient is equal to 0, or the algorithm will generate a sequence xk that has the property that limit infimum of the norm gk must be equal to 0. The first case will happen in the case when algorithm has a finitely many successful iterates, and the case 2 is for when the algorithm has infinitely many successful iterates. For the first case, when the algorithm has finitely many successful iterates, if the trust region algorithm has finitely many successful iterates, then in that case let us assume that k naught be the last successful iteration index. Then certainly we must have norm gk naught plus 1 is equal to 0. We claim that norm gk naught plus 1 must be equal to 0, because if this norm value is not equal to 0, then we can keep shrinking the trust region radius, and after certain index number again the trust region radius will be less than a threshold given in the previous result, and we will certainly get then an index, some index k dash which is bigger than k naught plus 1, so that at k dash you will have a successful iterate, and that is contradictory to the assumption that k naught is the last successful iteration index, and therefore evidently you must have this norm of gk naught plus 1 is equal to 0, and that is your part 1 of this result. Part 2 is the case when the algorithm generates an infinite sequence. If the trust region algorithm has infinitely many successful iterates, say the sequence xk, where k is belonging to some index set lambda, say, we prove that the limit infimum of norm gk must be equals to 0, where k tends to infinity but k must be lying in the index set lambda. Here we notice that without loss of generality we can just simply take this lambda to be the set of all natural numbers, and accordingly we will not have to write every time this k belonging to lambda. Or instead let us consider to write this sequence by some other index j. By j we mean a general index for the successful iterates. As we have used k for any general iterate, we have used here j for referring a successful iterate. So let us try to prove it. We shall prove this result by the method of contradiction. If possible, suppose, if possible, let this limit infimum is not equals to 0, then certainly we have at least one epsilon greater than 0, such that for this epsilon greater than 0 we have an index capital K such that the norm Gj is greater than or equals to epsilon for all j greater than equals to capital K. Here we see that the sequence xj is a sequence of successful iterates, and therefore if we consider two consecutive successful iterates xj and xj plus 1, then the reduction ratio at the jth index, that is rho j, must be greater than or equals to eta 1, and therefore we have if xj minus if xj plus 1 is greater than or equals to eta 1 times the predicted reduction at the step pj. As pj is such a step in this theorem at which the model function value is less than or equals to the model function value at the Cauchy step, we certainly have this right hand side quantity is greater than eta 1 times half into norm gj into minimum of delta j and norm gj divided by norm bj. And as after the index capital K we have norm gj greater than equals to epsilon, we have this right hand side quantity further greater than or equals to eta 1 times half epsilon and minimum of delta j and epsilon divided by beta, where beta is an upper bound of norm of bj's. And due to this inequality we can find that if x1 minus if xj plus 1 is equal to, by the telescopic sum, that from I equals to 1 to j, if xi minus if I plus 1, which is then greater than or equal to half times, here we are executing j many times this summation, so half times eta 1 into j into epsilon into minimum of delta j and epsilon by beta, and therefore this gives us minimum of delta j epsilon by beta is less than equal to if x1 minus if xj plus 1 divided by half eta 1 epsilon times j. As the function f is assumed to be bounded in the initial level set L0, this quantity further is less than equal to some constant divided by j, which tends to 0 as j tends to infinity. And therefore what you have is that delta j is tending to 0 as j tends to infinity. So what we get is that norm gj is not equal to 0, norm gj is greater than epsilon, but you have delta j is converging to 0. This will not certainly happen due to the node that we have mentioned just before this global convergence result, and therefore our assumption that limit infimum of norm gj is wrong, and hence the part 2 of the result is followed when the trust region algorithm has infinitely many successful iterates. This ends the global convergence of the trust region algorithms. Here we notice that we have just assumed that The pk is such a step for which the model function value is less than equal to the model function value at the Cauchy step. And due to this inequality, the entire result is followed by the sufficient reduction property of the Cauchy point. In fact, the part 2 of the result can be replaced by limit k tends to infinity norm gk is equal to 0. The proof for this limit k tends to infinity norm gk equals to 0 can be found in the book of Sun and One. It was Professor Powell who proved that limit infimum norm is equal to 0 for the case when eta 1 is equal to 0. The essentiality of eta 1 has to be greater than 0 to realize limit k tends to infinity norm gk equals to 0 was first proved by S. Thomas in his PhD thesis in Cornell University. Well, these are all about the global convergence of the trust region methods, and we close here discussion of the trust region methods. For the further improvements, we notice that during the discussion of dogleg step or double dogleg step, we require the full Newton step. The full Newton step you all know is given by negative bk inverse gk, which requires that the bk matrix is invertible. In fact, in the discussion of dogleg and double dogleg, we have assumed that this bk is positive definite. When bk is not invertible, then here we can employ sufficiently large alpha greater than 0 for which bk plus alpha in is invertible. For example, we can choose this alpha value lying in between minus lambda mean to minus 2 lambda mean, where lambda mean is the negative most eigenvalue of the matrix bk. After modifying this bk by bk plus alpha in, we can follow the same process as we have followed in the dogleg step to identify a dogleg step lying in between the full Newton step and the Cauchy step. We notice that this identification of dogleg step is eventually taken place in the two-dimensional vector space spanned by negative gradient or gradient and bk inverse gradient. By observing this, we can identify dogleg step with lesser computational cost, which is known as two-dimensional subspace minimization technique, which was first found in this paper of Schulz, Scannable and Bird in the year of 1985. We also observed that so far in all the trust region algorithms, we require to solve the trust region subproblem, or we need to identify the full Newton step. Identification of full Newton step or identification a solution to the trust region subproblem require solving a system of linear equations, and therefore when the matrix capital BK is of high dimension, in that case the operation may be quite costly. To reduce this computational cost, in the year of 1983, Stihog presented a conjugate gradient method where a preconditioned and truncated conjugate gradient method have been employed, which solves the trust region subproblem approximately. This method is today usually called as Stihog conjugate gradient method, which can be found in this paper written in the bottom of the screen. For several other variants of trust region methods and their improvements, we refer to the book by Kohn, Gold and Toint, which is a richly detailed exposition on trust region methods. Interestingly, in this book, you will find a detailed annotated bibliography on the development of trust region methods. I end up the lecture here. On the next lecture, we will start discussing theories for constraint optimization problems. Thank you. Thank you all for all of your kind attention.